A flashlight bulb rated at 3.0 volts at 1.5 watts is connected to a rectangular circuit of wires of negligible resistance. The circuit is placed in a uniform perpendicular magnetic field of strength 0.10 Tesla. The right wire of the circuit, which is 10 centimeters long, is free to slide and is pulled at constant speed v through the magnetic field. What force is needed to keep the wire moving? Now we have to find what force we need to keep the wire moving. Now this is an important consideration because since there is an induced current in the wire, that induced current is going to experience a magnetic force based off of the fact that it's moving through a uniform magnetic field. So remember, a current-carrying wire experiences a magnetic force equal to the integral of the product of the current in the wire and the displacement differential of the current crossed with the magnetic field through which the current is moving. And this would give us the magnetic force acting on that current-carrying wire. Now, if the current is constant and if the magnetic field is uniform and if they are at right angles, all things we've talked about before, we would see that the magnetic force acting on the wire is equal to the product of the current in the wire, the length of the wire, and the magnitude of the magnetic field the wire is exposed to. Now, the direction of this magnetic force is the direction given by the right-hand rule acting on this wire. Now, the right-hand rule would say fingers in the direction of the displacement differential of the current, palm facing the magnetic field. The direction that our thumb ends up pointing is the direction of the magnetic force acting on that wire. So for this wire, and let's just illustrate the wire down here, this wire has a length L, and this is the movable wire. This wire is carrying a current up. So, and the magnetic field acting on the wire is pointing away from us. When we use the right-hand rule, by sticking our fingers in the direction of the current, facing our palm in the direction of the magnetic field. So right now we are looking down on top of our hand. Notice that the direction of the magnetic force is straight to the left. This is the direction that our thumb is pointing. So the magnetic force acting on this wire is actually to the left. So what that means is if this wire was moving with the speed of v, it would slow down and stop because of that magnetic force that's directed to the left, opposite the velocity. So we have to apply an external force to allow this wire to move at constant speed. So let's figure out what that external force needs to be. I'll label that external force in this picture. This external force we will call the pulling force, F sub P. And this pulling force has to be equal in magnitude to the magnetic force acting on the wire in order to keep it moving at constant speed. So that means that this pulling force is just simply the product of the current in the wire, the length of the wire, and the magnetic field. We know the length of the wire. We know the magnitude of the magnetic field. We don't know the current. However, we do know that the current induced in a conducting loop moving through a uniform magnetic field is equal to the induced EMF over the resistance. And that induced EMF, remember, is equal to the product of the conductor's speed. In this case, this is the speed of the moving wire, the length of the wire, the magnitude of the magnetic field, divided by the resistance of our circuit. Now, we could actually save ourselves some time because remember, the induced EMF is just the potential difference needed to light this bulb to maximum brightness. And we know that that potential difference is delta V. So it's that potential difference divided by the resistance of the bulb. And to find the resistance of the bulb, we could turn to this relationship between the power of our bulb, the potential difference the bulb needs to light at that power, and the resistance in the bulb. This tells us that the resistance is equal to the ratio of the square of the potential difference over the power of the bulb. So we could plug this into our expression for current. This would give us that the current is equal to the potential difference over the resistance, but the resistance is equal to the potential difference squared over power. We see a potential difference in the numerator cancels with the potential difference in the denominator, and this ends up being current is equal to power divided by potential difference. Oh, and you know what? We really should have seen that earlier, because remember, power for an electrical component is equal to the product of the current and potential difference. So current, of course, is going to be equal to the power of the potential difference. So at least this is a good confirmation of the work we've done. Current is the power over the potential difference, and we verified that by using the information we have. So we now have an expression for the current. Now that we have an expression for the current, we could use that to find the magnitude of the force that we need to pull with in order to keep that wire moving at constant speed. Now remember, the pulling force was equal to the product of the current, the length of the wire, and the magnitude of the magnetic field. So this means that the pulling force is equal to the current, which is the power over the potential difference, times the length of the wire, times the magnitude of the magnetic field. The pulling force is equal to the following: the power of our light bulb, which is 1.5 watts, divided by the potential difference needed to light our light bulb at 1.5 watts, which is 3.0 volts. This is multiplied to the length of the wire, which is 10 centimeters long, and the magnitude of the magnetic field, which is 0.1 teslas. After doing my unit check and plugging this into my calculator, I get that the magnitude of the pulling force is 5 times 10 to the minus 3 newtons, or 5 millinewtons. So we have to pull our wire with the force of 5 millinewtons to the right in order to keep the magnetic force acting on the wire from slowing the wire down and stopping it.